Math 1314, Tyler Junior College, Section 4.5, Exponential Growth and Decay. Exponential growth example. In the previous video, we defined the form of an exponential growth or decay model as a function. It's not actually defined, it's a consequence of what we mean by exponential growth and a little bit of calculus. In this video, I'd like to go through an example using actual data that I found on the internet. In the year 2000, the world's population was approximately 6.127 billion. In the year 2010, it was approximately 6.916 billion. We're going to do two things. A, we're going to build an exponential growth model. B, we're going to predict the population in the year 2050. And I think I'm going to tack a third thing on here. It might drag the video out, but I think it's an important exercise. Predict when the population will reach 12 billion. Now, who would want to know something like that? Well, anybody who's concerned about the planet's resources, anybody who's concerned about there being enough space for people on the planet. I'll admit that our population cannot continue to grow infinitely simply because of the math. Each one of us takes up a certain amount of space, and there's a finite amount of space on the planet. So at some point there's for lack of a better word, breaking point or a limiting population. But let's see if we can tackle all three of these. First, let's build the exponential growth model. Now, how are we going to build the model? Well, we know the model has to look like this form. F of t equals an initial population times e to the bt power. But in order to build a model, we have to first define a starting point in time. In an example like this, it's usually the earliest year that you're given. In this case, it's the year 2000. So we're going to let t equal the number of years after 2000. And by the way, I don't want to mislead you into thinking that the time always has to be measured in years. It can be measured in any increment, months, days, seconds if you want to. Some things grow or fast very quickly and you have to measure them in a much smaller amount of time. But what is f of t going to measure? Now, you might say the current population. Well, true. But notice that our populations were given in terms of billions, and so it makes sense for our function to measure the population in billions. This is a common approach to problems involving large numbers. Don't use the numbers themselves, use them in terms of a larger unit of measurement. Or if you want to, you can write 6,120,000,000 and 6,916,000,000. So if you really want to do a lot of math with 10-digit numbers, knock yourself out. I'm not going to. We'll just scale it down to billions. How are we going to find this model? Well, we have to find the two variables that we don't know. But one of them we already do. Remember that A0 represents the initial population, or the population in the year that's being referred to by t. In this case, the year being referred to by t is the year 2000, and the population in the year 2000 was 6.127 billion. So out of nowhere, we get that A0 is 6.127. I don't have to write the word billion because I'm already measuring in billions. But what about the B? Well, the B represents the growth rate, but it's not as simple as simply calculating by what percent did the population increase. In order to calculate the B, we're going to have to set up and solve an exponential equation. How can we do that? Well, take advantage of the other initial condition. In the year 2010, the population was approximately 6.916 billion. This means that when I put in the number that represents the year 2010, I'm supposed to get an answer of 6.916. What number should I put in for t to represent the year 2010? Since t is measuring the number of years after 2010, I can simply subtract these and figure out that t equals 10. So that second statement about the population in the context of our model can be written as f of 10 equals 6.916. But I know what my function looks like. It looks like this, and on top of that, I know what the leading coefficient is. So why don't we go ahead and write our function 6.127 e to the, we don't know the b, but we know it's getting multiplied by the t, which is 10. I know writing b times 10 looks funny because normally it would be written 10b. In the next line, I'll write it as 10b. Well, now we have an exponential equation, and we're solving for the variable in the exponent. We have a strategy for that. If you don't know the strategy, I suggest rewatching the video series for section 4.4, especially the ones about exponential equations with unlike bases. I forget which number it was in the series, but you can find it. The strategy, however, was to isolate the exponential term, which is e to the b times 10 power, and then hit both sides with a logarithm. If we're going to isolate this, we need to divide both sides by 6.127. And we get e to the 10b, told you I was going to write it that way, is equal to whatever this answer is. Now here's where you have to make a decision. Do we want to divide this and round it off, or do we want to leave it alone? My advice is don't round anything until it's absolutely necessary. The more you round internally, the more incorrect your values are, and the more moves you do to incorrect values, the more incorrect they become. So I would leave this alone. I would not do anything with it yet. I want to wait till the last possible moment to get out the calculator. 6.127. Okay? The next move in solving this exponential equation, once you isolate the exponential term, is to take the log of both sides. And you can choose any base you want. But as was mentioned in this video series for 4.4, if you're going to use a log and there's an e, you should use natural log. If we take the natural log of both sides, we get the natural log of e to the 10b power equals the natural log of 6.916 over 6.127. The purpose of taking the natural log was to use the power rule and bring the power down off of the argument over here. When we do that, we'll be left with the natural log of e, which is equal to 1. So the left side simplifies all the way down to 10 times b. Still equal to the natural log of this fraction. 6.916, 6.127. At this point, I'm only one move away from figuring out the b. Divide both sides by 10. And we get b equals the natural log of 6.916 over 6.127. And then all of that is over 10. Since we're done solving for b, now's a good time to get out a calculator. Let's take it to 4 decimal places. Let's see here. Natural log of 6.916 divided by 6.127, close parentheses, divided by 10. And to 4 decimal places, you get 0.0121. And that gives us the missing piece of the model, the growth rate, if you will. That growth rate means that this population is increasing approximately 1.21% per year. Now that we have all the pieces of the exponential model, let's actually write our exponential model. The initial population was 6.127. Remember, that represented billions. E to the b times t. There's the b, 0.0121 t. And we now have the answer to part A. If you do several of these, you start realizing I'm just repeating the same moves over and over, and you can actually make a generalization about how to calculate b by just looking at the pieces here. Population after a certain time, initial population, amount of time that's elapsed. So it's not that hard to make a generalization to calculate the growth rate in an exponential model if you have 2 populations, one at the beginning and one at a future point in time. All right. Part B, let's predict the population in the year 2050. function does precisely this. It predicts populations, but recall, and it's been erased, that t equals 0 was the beginning of this model in the year 2000. What would t equal in the year 2050? Well, if t was measuring the number of years after 2000, then t would equal 50. So all we have to do is put 50 into the function and see what comes out. 6.127 e to the 0.0121 times 50. Again, this is just calculator button pressing, so I hope you're comfortable with your calculator. 6.127 times e to the 0.0121 times 50, and we get approximately 11.22. Does that mean that there's only 11.22 people on the planet in the year 2050? No. Remember that our function was measuring the population in billions. That's a lot of people. Initially, this started with 2 parts, but I wanted to do a third part, predicting the population will reach 12 billion. Well, it's almost there, so it shouldn't be too much longer. Why 12 billion? Somewhere I heard that that was the tipping point between the population being able to survive. I don't know how true that is, but 12 is a nice round number. So how are we going to find when the population will reach 12 billion? Well, we're trying to answer the question when, which means at what time, which is being measured by t. So we're solving for t. The 12 billion represents the output of the function, so we need to solve f of t is equal to 12. Well, that's not too hard to set up. We already know what the function is. 6.127 e to the 0.0121t, but we want that to equal 12. We just solved something like this a minute ago, except we solved for b, but structurally it was the same. Number, variable. Since we've just done that, I'm going to go ahead and accelerate to what you would get if you solve this. I'll describe how you would do it though. You would divide both sides by 6.1. In fact, let me start building the solution based on what I would do. You would start by dividing both sides by 6.127. So this is the first thing that would happen to the 12. Then you would take the natural log of both sides. The consequence of that is it would cancel the e and you would be left with 0.0121t, at which point you would just divide. If you're going into an area where you do a lot of mathematics, you start looking for opportunities to streamline processes, but it's important to point out that you don't want to streamline processes at the expense of accuracy. So I would be very careful trying to do what I just did until you're 100% confident. But if you're doing it on a test, I wouldn't. The less work you show on a test, the less partial credit we can give you if something goes wrong. But I would bet my job that what I just wrote there is correct. Unless I miswrote something, which I don't think I did. Let me make sure I typed it in correctly. Natural log of 12 divided by 6.127, all divided by 0.121. All right, so the answer is about 55.6 years after 2000. So the year 2055, somewhere between June and July. It'd probably be somewhere in July because the end of June is exactly half a year, aka 8.5. So somewhere in July or August of 2055. Now you may be questioning, is this really going to happen? Well, probably not, because nobody can accurately predict the future all the time. If you could, you could get super rich and then you could rule the world. But the truth is, there's more to trying to predict the future based on past data, because you can do it with more than just 2 data points. We may talk about that in the last video. I make a note here about models. It won't be really something to do, it'll just be a point to make. All right, in the next video, we'll take a look at an example of exponential decay.